Alright, today we're doing expected frequency, which carries fairly easy calculations, but I think the main point of today is more in how to interpret and how we use that word expected. So say we take a coin, we know that the sample space is very simple. When you flip a coin, you've got heads and tails, and each one happens with probability 1/2. And so your sample space divides evenly into two outcomes, heads and tails. And the idea of expected frequency is in trying to do some sort of merge between the theoretical and the experimental probability. So if we were to say flip this coin 10 times, we would expect that about half-half, heads and tails, would happen. So it would spread out a bit evenly like this. And what we say is we expect this half-half split, half of 10 being 5 heads and 5 tails. Now, that's as simple as the calculation is, but I want to clarify what we mean when we say expect, because we don't actually literally expect 5 of each, right? You don't need to know this, but the actual probability of getting exactly 5 heads and 5 tails when you flip the coin 10 times is only about 25%. So actually, we're not saying that when you flip a coin 10 times because the chance is 1/2, we're not saying that it should end up as 5 heads, 5 tails. We're not even saying that it's likely to end up 5 heads, 5 tails. It's actually not likely that it'll end up that perfect, right? But mathematically, based on theoretical probabilities, we mathematically expect it, right? It's a bit weird because it's like we don't actually literally expect it, but we mathematically do. And like we did with the experimental probabilities and playing with the dice last time, the more times you flip the coin, the closer the results you get will align with the expected value, right? So it's more like in the long run, over a long period of time, repeating this experiment many, many times, we expect that about half of them will be heads, about half of them will be tails. We are in no way saying that it should be or that it's even likely to be. Okay, it's just approximately we expect that it should end up a little bit like that, assuming the coin is fair. Okay, so to generalize the calculation, when we repeat an experiment, the number of times we expect a certain outcome to happen is its probability multiplied by the number of times we did the experiment. Just as our half times 10 equaled 5, and we expected about 5 heads and 5 tails. Okay, so we just multiply the probability by the total number of attempts that we had. Alright, an example of this to finish. It says a die was rolled 72 times. The results are shown in the table that I've put in the bottom left corner, and we're answering those questions. So start with part A, find the value of A. Now we're told the die was rolled 72 times, and all those frequencies are in the table already, which means they need to total to 72 altogether. And so what that tells you is A, which is how many times the number 3 appeared, must be the total 72 minus the rest of it to see what's left over. All right, and so we find that A must be 10 in order to add up to 72 with all those frequencies. All right, part B, what's the relative frequency of obtaining a 4? This is what we did last time. Obtaining a 4, well, if you look at the number 4 in the table, it's got a frequency of 8, which means the number 4 appeared 8 times. And it appeared 8 times out of the 72 rolls altogether. So that gives you 1 out of 9 as its relative frequency. Okay, and part C tells you that the die was unbiased, and it's asking for the number, which is the score, which was obtained the expected number of times. Okay, so while in part B, we got the relative frequency to be 1 in 9, we're told, well, the die is actually fair. So the theoretical probabilities actually 1 in 6, not 1 in 9. All right, and so the die being unbiased means everything's equally likely. The chance of each number appearing is 1 in 6. And so the expected number of times that each number should appear is 1 in 6, the probability of it appearing, multiplied by the number of times it was rolled, which for us is 72. So the expected number of times each number appears, we'd expect, right, that in 72 rolls, each of them appears 1/6 of the time, so we'd expect for each of them to appear 12 times. Right. And again, that expect isn't as though we were really sitting there thinking that every number would appear 12 times. Again, it's a mathematical expectation, not a literal, like, real-life expectation. Okay, so mathematically, we expect that 1/6 of 72 is 12 times for each number. And so you scan down the table and see, well, which number actually appeared 12 times, right? Which number was obtained the expected number of times. And we find that 12 appears here, which is the number 5. And so the answer to part C is 5 was the number that was obtained the expected number of times. Okay, so that's all for today. Thanks for watching, and have a good break. See you later.